So this is lecture 1 for geometric methods in algorithm design. I'm taking this course in spring 2025 and this is my attempt to teach the material that I learn for my own understanding, and maybe I'll look this material up later in life or whenever. So today we are learning the first lecture of geometric methods in algorithm design, and we are going to talk a little bit about NP-hard problems, specifically the vertex cover and the traveling salesman problem. And we'll talk about the notion of approximation and what 2 approximation or 1.5 approximation here means. Then we'll look at linear programming, another approach to approximation, and we'll see its application to vertex cover, and we'll talk a little bit about integrality gap. And then we'll do a little conceptual dive into LP, as in why linear programming works, and we'll demonstrate that with the ellipsoid method. So NP, well, if you have seen my other videos on NP hardness, NP complete, whatever, is non-deterministic polynomial. So class P means a deterministic Turing machine can solve the problem in polynomial time. NP essentially means very hard to solve. There is a technical definition of NP that is that it's polynomially easy to verify but not solve. So it's something technical, but it essentially means that it is very hard to solve. So that's what makes possible the field of cryptography, because it's so hard to solve that for, let's say, 1,000 input graph, it's just not solvable accurately. So we can't solve it accurately, but can we try to give a good enough solution, something which is not too bad, but it's obviously not accurate, like exactly 100% accurate. So enter the field of approximation algorithms. So let's talk about vertex cover, NP complete problem. So let's say I'm given a graph. Choose vertices such that all edges are visible if you stand on those vertices. So let's say in this graph, if I choose these 2 vertices where the eyes are, I'll be able to see each and every edge standing on this vertex, right? An example of vertex covers, as you can see here, you can choose these 3 vertices and all of the edges will be visible. Similarly, you can choose these 4 vertices and all of the edges will be visible. From if you were a lighthouse on these vertices, all of the roads will be illuminated, so to speak. So the problem is that given a graph, choose the minimum vertex cover, basically the least amount of vertices which can cover all the roads, the least amount of lighthouses you need to cover all the roads, essentially. So this is an NP-hard problem. We cannot solve it accurately, but here's an approximation algorithm. Pick an arbitrary edge. So any vertex cover, if I have one edge, let's say I pick any arbitrary edge A. So any vertex cover must have at least one endpoint of this edge, right? Because if neither of those endpoints were there, then this edge is not covered. This edge is not lit up by any lighthouse, so it is not a vertex cover. So one of these 2 vertices must be there in a vertex cover. So let's take both endpoints for now. Remove all the edges covered by these vertices and then repeat. So I pick an arbitrary edge. I take both of those endpoints, both of those vertices, remove all the edges covered by these particular vertices, and then rinse and repeat. Continue until no uncovered edges remain. Well, why does this algorithm work? So in the end, when the algorithm stops running, I construct a matching. So what does that mean? A set of edges, no 2 of which share an endpoint. That is, a set of edges which are not, neighbors, which do not touch each other, so to speak. And why does that happen? Because when I pick an edge, I pick both of these vertices and I remove all the edges which are covered by these vertices. So if I pick an edge, by definition, when I pick both of the endpoints of that edge and remove all of those edges, I am basically removing all neighbors of this picked edge, basically. So this matching is maximal, which means as big as can be. As if I add another edge to this, I will find a common vertex with an existing vertex on this set already. So this set is as big as it can be. Now if I add all these vertices, basically I pick an edge, and I take both of those vertices. I remove all the edges spanned by these two vertices and I repeat. So if I add all these vertices, both endpoints for each edge in a matching, I am guaranteed to create a vertex cover, right? Let's think about it. Why are you guaranteed to create a vertex cover? Let's say you started with a blank graph, nothing. You pick an arbitrary edge and you select both of those vertices. So you definitely cover the edge you have picked, but then you also cover all the edges which these two vertices look at, and then you remove them from the graph altogether, and then you get started again on a blank graph, so to speak, right? So at every iteration of the graph, at every iteration of the algorithm, you remove a chunk of edges which you keep on covering when you select both of these vertices. So you definitely create a vertex cover. So if the algorithm picked k edges, the vertex cover found is of size 2k because I take both the endpoints. Now any vertex cover that I pick must have size of at least k, as it needs at least one endpoint for each of these k disjoint edges. So the k edges that my algorithm has selected are disjoint. They do not share any common vertex with each other, right? So if there are k edges, there needs to be at least k vertices in my vertex cover, because if I do not pick k vertices, there will be one edge for which both of the endpoints are not selected, and that is not a vertex cover, right? So it has to have k disjoint edges, and my vertex cover found is of size 2k. So therefore, at worst, my vertex cover is two times as bad as, you know, the real solution. So, you know, a lot of words, a lot of hand waving, but the key insight here is we never needed to know the actual value of the optimal solution, you know. We only needed a quantity to reason around it. And finding this quantity in an analysis is an art. And this quantity in this particular example was this matching of k edges. We never needed to know how big the vertex cover is, but we know that vertex cover has to be at least k. It cannot be less than k. And if we know that the vertex cover is at least k, and we know that our vertex cover is of size 2k, we can say that, well, our algorithm is at most twice as bad, cannot be any worse, right? So that's the first approximation algorithm. Pause and ponder over it for a while. So now we'll look at the traveling salesman problem. I personally find this problem really beautiful. So given a graph of cities and distances, between every pair of cities, so it's a complete graph basically, every two vertices are connected to each other. What is the shortest possible route that visits each city exactly once and returns to the origin city? So it's like travels every city once and loops back to the original city. That's the traveling salesman. And this is a NP-hard problem. It is very general actually and can be formulated even into be used as DNA sequencing. Works as long as the distance between vertices is a metric, that is, it's symmetric, like A to B and B to A is the same, and satisfy the triangle inequality. That is, A to B plus B to C is always greater than the distance between A to C. So that's called a metric traveling salesman problem. So let's give an algorithm for this. So start with the two closest cities such that Cij is minimum. The cost going from between I to j is minimum. And we at every iteration maintain a Tor on the current set. So first of all, the set is ij. So the first Tor on this set will be starting from I, going to j, and then going back to I. Basically saying that in my universe, let's say I only had these two vertices. So the traveling salesman problem is pretty easy. Start with one, go to the other, and come back to the first one. So at each iteration, find A, something that is in my Tor already, and something that is out of my Tor, such that CAB, the cost is minimum. So find a vertex A in my set S, B outside my set S, such that CAB is minimum. Now suppose the current Tor is something like blah 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 blah. The traveling salesman is at A, next he goes to K, and then so forth. So the algorithm is that insert B between A and K. So the Tor now becomes blah blah blah, everything stays the same, comes to A, goes to B, then to K, and then everything remains the same. So stop when all cities have been added to the Tor. This is a 2-opt algorithm. Let's think about it. Let's think about why this works actually. So at every iteration, whenever I find CAB such that CAB is minimum, whenever I find an edge AB such that CAB is minimum, this kind of reminds me on how we construct the minimum spanning tree in Prim's algorithm, right? Every time we find the edge which is of the minimum cost and we keep adding it to our existing tree. Something reminds me of that here. But what instead what we do is we also insert it in between the A and K. So A to B, B to K is the new length, but previously it was A to K. But now because this satisfies the triangle inequality, A to B plus B to K is only greater than A to K. And well, I'm not going to give the proof exactly, but it follows these ideas that we form a minimum spanning tree, and a tree has to be always greater than a tour because a tree visits every node once, etc. And I'll make another video on the actual analysis of the traveling salesman problem, but this is a 2-opt algorithm. And as you can see, the slide is blank because I'm lazy. Now there is another algorithm called the Christofides algorithm, which is a 1.5-opt algorithm, and it follows from the same ideas. That is, if you can form a tree, the size of the tree can only be less than the size of my tour, like any tour. So the minimum spanning tree will always be less than the traveling salesman tour. So if I can find a way to approximate the minimum spanning tree easily on this particular set, I'll be able to do the same for the traveling salesman. So Christofides algorithm does the same. It forms a minimum spanning tree, and then it forms a tour around all the leaves and all the odd degree vertices, and they do an alternate coloring and so forth. I mean, we don't need to get into the details, but anyway, the idea is that there are NP-hard problems, and then there are approximation algorithms, which are, which give a reasonable guarantee. Like the vertex cover can only be twice as bad as the actual optimal solution, and the Christofides algorithm can only be 1.5 times as bad. So now let's look at linear programming. Now what does that mean? Another approach to approximation. So let's say I completely forget I'm a programming language. Let's say I do not understand English, and all I want to do is talk about variables. So let's say for a vertex cover problem, I assign an indicator variable xv to each vertex v in the graph, right? This indicator variable is 1 if the vertex is included in the vertex cover, 0 otherwise. Now the objective of the vertex cover problem is to minimize the number of vertices in the solution, or speaking in math, minimize the sum of xv over all vertices, where xv is 0 if my vertex is not included, and xv is 1, exactly 1 if my vertex is included, right? So the vertex cover is minimized when the sum of all of these included vertices are minimized, essentially. So now remember the edge visibility aspect of the problem too. I mean, I could assign all of them to be 0. That means select no vertices, but that's not a vertex cover. So for every edge uv, at least one endpoint must be in the vertex cover, right? So for every edge uv, either xu is 1 or xv is 1 or both. Basically, for every edge uv, xu or xu and xv, for every edge uv, xu and xv cannot be 0. Like both of them cannot be 0. One of them at least has to be 1. Only then that edge is covered, right? Because one of the endpoints has to be included in the vertex cover, or both. I don't care about that, but one of them has to be. So for every edge, let's say if I make this constraint that xu plus xv must be greater than equal to 1. That actually makes sense. So minimize the sum of all xv or all the vertices such that for every edge xu plus xv must be greater than equal to 1, right? It can be 1 or 2, basically, if both are 1. So yeah, that makes sense. So here's the integer program. The objective is to minimize over all the vertices the sum of their indicator variables, subject to these constraints, such that for every edge uv, xu plus xv must be greater than equal to 1, and xv is either 0 or 1 for all v or for all vertices. So the objective minimizes the total number of vertices in the cover. The constraint ensures that at least one endpoint of every edge is included in the cover. The binary constraint reflects whether a vertex is part of the cover or not. So if when it's x1, the vertex is part of the vertex cover. When it's 0, it's not. So all I've done is just reformulated the vertex cover problem in mathy terms, in optimization terms, rather than saying it in English. So obviously it's an NP problem. I'm not going to be changing that aspect of this problem just by stating it another way. However, there is this thing called LP relaxation. So I minimize the XVs over all vertices, everything stays same. For every edge, XU plus XV must be greater than or equal to 1, that stays the same. But now I can let my XV range from 0 to 1. Like instead of having a binary constraint, either be 0 or 1, I can let my XV take real values between 0 and 1. So in LP relaxation, the binary constraint is replaced with a continuous constraint. This allows fractional solutions, making the problem easily solvable using optimization techniques. So let's say you give an arbitrary graph and you solve this particular problem. You will get solutions like, oh, let XV be 0.33333. Let another XV be 0.333, and then let another be 0.7773, whatever. So that's not the real solution, but it allows a fractional solution. But how do we use these fractional solutions to get back a vertex cover? Well, the answer is we round. So if in the resulting solution, I'm calling it x star, if in the resulting solution xv star is greater than half, we make that 1, and if it's less than half, we make it to 0. Basically simple rounding of those variables. So let's first verify that this rounding is at least a vertex cover. So consider an edge E. The only thing we need to do to verify is to see if it satisfies all the constraint, right? So consider an edge E, UV. By feasibility of x star, the solution, it's feasible because it was returned as solved by the linear program, right? Like by an optimization method, whatever. By the feasibility argument, for x star, for every edge UV, XU star plus XV star must be greater than 1, because that's the constraint that we enforced. So that means either XU star must be greater than half, or XV star must be greater than half, or both. Basically, not both of them can be less than half, because if both of them were less than half, then this couldn't have been greater than 1. So at least one of them will be rounded up to 1. So that satisfies the integer constraint too, actually. So when I do this rounding business, I am not violating the integer constraint. So I solve the linear program and then I round it, I still get a vertex cover. So now let's see how bad this is. We already had a 2-opt solution before, right? Let's see how bad this linear program solution is. So LP finds a solution over a larger space, the continuous interval instead of the, discrete finite interval. Therefore, the LP has to be less than or equal to the optimal solution of the graph, right? By virtue of the fact that LP is doing the search over a unit cube, whereas the integer would only do the search on the edges on the vertices of that cube, right? Because LP does this search for the ideal solution over a bigger area, it cannot be worse than the opt, right? Because the solution space of the opt is a subset of the solution space of the LP. So the LP has to be less than or equal to opt. That's equation number 1. Now let's bound the weight. So LP of G is sum over all the vertices XV star. Now let's say I chose only those vertices which I put into S, right? And all of their weights must have been greater than half. So this has to be greater than half times XV, all of them which were included in the solution by rounding, right? And that is half the weight of the solution. So essentially, the LP is also greater than half the weight of my solution. So half the weight of my solution is less than LP, which is less than opt. So weight of my solution is less than 2 opt. Let's reason about this once again, okay? My LP solves, this is XV star, the one which is returned by the LP, over all the vertices. That's what it solves. Let's say I do not look at all the vertices which are less than half. I only look at the vertices which are greater than half. And their XV, their value after rounding becomes 1, right? So let's say in my capital set V, capital V, I had a bunch of vertices, some of which were less than half, some of which were greater than half. I only look at those which are greater than half, and I say that all of them are greater than half. So that's what I'm saying here, that they are greater than half, all the vertices that were selected in my solution, and xv, where xv for this is actually 1, because now I'm rounding it up to 1. So this is basically just 1/2 times the weight of my solution, the weight of the solution which is returned by the rounding, after rounding. So my LP is greater than half of the weight of the solution, and it is less than opt. That means my weight of the solution is less than 2 opt. Again, a 2 approximation algorithm. I'll give it a moment if you want to ponder. This is essentially the argument here, that instead of summing over all the vertices V, I only sum over all the vertices which I put in the solution. I discard everything else, and because all of them were positive, it can only decrease the value. But then the vertices that are selected could be values like 0.6, 0.7, 0.55555, 0.8, but they're definitely greater than half. So I select those vertices, I lower bound them with half, because that's what I did. Whenever they are greater than half, I make them 1. Whenever they are less than half, I make them 0. So whenever they are greater than half, I make them 1. So xv here is 1. Only for those vertices which have been selected by the algorithm to be greater than half. This is a very, simple statement, but it is kind of like elegant. But yeah, that's about it. So half of the weight of my solution is less than the LP, which is also less than the opt. So weight of my solution is less than 2 opt, which is desired result. So let's talk about this notion of integrality gap. So in an instance, let's only talk about in the instance of a minimization problem. Let m int be the real minimum of the integer program, which we did not know. Let m frac be the relaxed minimum, which is the minimum of the linear program relaxation. So the integrality gap of that instance is defined as the integer solution divided by the fractional solution, the magnitude. So the integrality gap is a concept very specific to LP relaxation. It measures how much worse the integer solution can be compared to the relaxed LP solution. So typically the integrality gap translates into the approximation ratio of the algorithm. In this case, the integrality gap here is 2. Basically, opt is m int, and m frac is the LP value, right? So the integrality gap typically translates into approximation ratio of the algorithm. That's a fact, just remember it. So now we'll get to this very interesting notion of the ellipsoid method. Basically, now you might ask, okay, how do you guarantee that you can solve the LP in, let's say, polynomial time, or let's say fast enough? So that's where the ellipsoid method comes in. So I'm just going to reformulate all of my linear program in terms of vectors. So find the vector x that minimizes C transpose x subject to some constraints ax greater than b. You can also have equality constraints here, doesn't change the fact. So C transpose x, what does this mean? So here the minimization was just the sum over all xv's, right? So if I put all of these xv's in a column vector and call it x, C transpose is another weight vector. So if in the vertex cover problem, C is just 1. So C transpose C is just the vector of ones, like unit vector, so to speak. Just a vector of ones. So this is just the sum over all x. But in a general scenario, C could contain weights, let's say. So x is the decision variable vector. C transpose x is the objective function that needs to be minimized. And ax greater than b is just constraint inequalities, where a is a matrix and b is a vector. So for let's say for my vertex cover problem, every row of my matrix A would represent every edge. It would mostly be zeros, but there would be some ones somewhere sprinkled. Like for every edge, I will look at xu plus xv, it should be greater than 1. So x, some of just those columns corresponding to xu and xv will be 1 in A, and everything else will be 0. So the key insight for this argument here is that we can formulate an optimization problem as a feasibility search by introducing a constant, let's say capital B. So choose a B and look for a feasible solution for C transpose X less than B and AX greater than B. If a feasible solution is found, let's say if I find even one X which solves this, let's see that C transpose X is less than B and AX is greater than B, I can decrease B and start again. Example B half, like I make B equals to B half and then repeat. So if no feasible solution is found, then take the intermediate value of B and continue. So what I'm doing is I'm essentially doing a binary search on B. So let's say I start with I'm given a very small graph and my ellipsoid method starts with a constant B as 1 million. Well, I can make all of the vertices as one and satisfy this constraint, and obviously 1 million will be satisfied. So now I make it 500,000. That is satisfied. Now I make it 250,000. That is satisfied. Boom, 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 boom. I keep coming down to, let's say now my B is 50. Oh, that is not satisfied. So now I go to 75. That is not satisfied again. Oh, I make it 80. That's not satisfied. I make it 90. That's satisfied. So now I make it 85. That's not satisfied. So now I make it 87.5, so to speak. Basically, all I'm doing is doing a binary search on B and trying to find if I find a feasible solution again and again and again. And the hope is that after a point in time, I will absolutely nail the exact constant B and the exact X for the feasibility one. So the optimization problem can be transformed into a feasibility search for a new set of inequalities. That's the key idea. So let's say the set of inequalities forms a polytope. A polytope is just a convex figure in a convex linear type figure in higher dimensions, right? So here X is like, let's say 1,000 node graph. So that is a 1,000 dimensional search. So our goal is to determine if the polytope has any volume inside. That means if it has any feasible solution. If it has no volume, then there could not have been, like, it's a zero, like there are no points which satisfy any of those constraints. So there are no feasible solutions. So this is what a polytope might look like in 3 dimensions, but that's, something very general. So let's start with a sphere, initial sphere. Start with a very large sphere, which, let's say we are domain experts and we gave that sphere a very large radius, such that we can be more or less sure that my polytope lies inside that sphere. Entirely inside that sphere, such as in this diagram. Now the key insight is, if the system is feasible, there must exist at least one inequality that is violated by the center of the ellipse. So for example, this is the center of the ellipse. It does not lie in the feasible area. So it violates at least one of the edges of the polytope, right? To address this violation, we shrink the ellipsoid to discard the bad half where the violation occurs. So here's the graph. Here's a figure. Let's say this is my polytope and this is the center of the ellipsoid, right? XT. And let's say I look at this particular constraint as A prime X greater than B. Obviously my center violates this constraint, right? So I'm sure that my real solution, my actual feasible solution, if it exists, should lie in the right half. So I do not need to know the left half's need to be concerned with the left half at all. So what I'll do is I'll chop this ellipse into 2. The one which is shaded is the one where my potential solution could lie, and the one which is not shaded, I am sure is just useless. So I'm going to create another ellipse which contains this point, and is tangent to this point. I do not know how mathematicians do it, but I'm sure they can. And then they form a new ellipse, and then they get a new center, and then we do the same thing on repeat. If that center lies in my polytope such that here, then I can conclude that, oh, I have found a feasible solution, I am done. If it does not, I keep on doing it again and again. So by iteratively shrinking the ellipsoid, we eliminate infeasible regions and refine the search for a solution. So here the key insight is, every iteration we also reduce the volume of the ellipse. So by reducing the volume, I am like kind of making that claim that if I keep on reducing the volume and I get to 0, that means there must not have been any feasible solution. But if I keep on reducing the volume, and there was a point when I landed in the center of my figure, or like inside my figure, that means I have found a feasible point. So this is how it would look like. Let's say I have a sphere like this. This is my center, and this is the polytope which I'm trying to, reach. Like try to see if there is a feasible volume inside it or not. I evaluate the center at, let's say, this particular constraint, and it does not satisfy it. So I do not need to worry about the unshaded half of my sphere. I could form an ellipse with this point, and being tangent to here, and it has a new centroid here. And let's say I evaluate this ellipse again on this particular constraint. It violates it. I form another ellipse which touches these points, and then it has another center which violates the polytope properties again. So I discard the half again, the left half again, do that once more time. I did not find a feasible solution, so I do it again, and I cut it into half again, form another ellipse. Oh, so close. Cut it into half again, form another ellipse. Again, very close but not quite. Cut it into half again, form another ellipse, and now we have landed inside the polytope. So now I can conclude that, okay, damn, I am inside the feasible region, so there must be a feasible solution, and keep doing it again and again while this binary search idea. So yeah, I mean, that was I wish I could give the metric TSP algorithm. That is very beautiful, but I gave the vertex cover to opt metric TSP. Just take my word for it. There is a 1.5 half Christophidis algorithm. I talked about linear programming, that is integer programming, and how integer programming can be relaxed to form a linear program, and how you would round a linear program, especially for the vertex cover instance. Also, I would like to emphasize that rounding a linear program is not that easy to do. Like from my own studies, I have found it, you have to be a little bit smart when you round the linear program. Like there needs to be some sort of expertise into that. And while linear program works, we showed that we showed this with the demonstration of the ellipsoid method. Ellipsoid method is not, I don't think, is used to solve actual linear programs, but it can be solved. It is a claim that linear programs are solvable, and this is the idea of shrinking that volume iteratively until you land inside a polytope. And when you are inside a polytope, you are happy because now you have found a feasible, and you keep doing it again and again for the binary search paradigm. And there was a discussion in class about that this is a polynomial time algorithm, and that included the notions of how much information you need, like in terms of bits and everything. And I don't remember it. I don't think it's as important. I'll just take professor's word for it that yeah, LPs can be solvable in polynomial time. So yeah, that was lecture number 1, and every week I'll make slides and I'll keep uploading them for the next couple 13-14 weeks for my semester. Hopefully by teaching I remember most of the stuff that was taught in the class, because I love this material. It's beautiful. So thank you.